From an early age, we all have experience with objects being thrown through the air and falling to the ground under the force of gravity. Even a 2-year-old child can develop an intuition about how the path of the ball through space is a function of time. Its trajectory might depend on how hard the object is thrown, at what angle it's launched, whether there are objects that might intercept it on its path, etc. Indeed, a vast number of sports involve kicking, throwing, headbutting, hitting, shooting, or launching a projectile, usually a sphere, but arrows, discuses, shuttlecocks, and many other shapes are used, with the goal of controlling its trajectory towards a target, goal, hoop, hole, or basket.
This is impossible.
And often in the performance arts, the projectiles are human beings themselves. And the applications, of course, go far beyond recreation. In warfare, ballistic missiles and artillery shells and bullets whiz about under the influence of gravity. Space exploration often begins or ends with some amount of coasting under the influence of just gravity. And in biology, there are numerous examples of leaping or flapping or squirting to effect a free fall through the air. And in practical matters, we care a great deal about whether the cargo drop is made from the plane at the right time, whether the nozzle pressure at the fire hydrant can get the water into a third-story window, and whether drag will be enough to cause a virus to be settled on the ground at a safe distance after a sneeze. We are therefore most interested in how projectiles move through space and time, both the parametric equations, r of t, and their trajectory. We're also interested in some general questions. How long is it in the air before hitting the ground or some object? How far away does it land? What maximum height does it reach? And how do these depend on launch speed and angle or other parameters of the environment? Here we aim to look at some of these questions from the perspective of physics, but in increasingly sophisticated, indeed ridiculously overkill in some cases, methods. At each point, we must examine the assumptions of physical theory before us and imagine how it might affect our results. We will sometimes recover our initial intuitions and sometimes find surprising new behavior. Hopefully, the sheer number of angles from which we can approach the same basic problem impresses the reader with just how versatile and ubiquitous an understanding of projectile motion can be. We'll begin with an examination of the ideas of Aristotle from the 4th century BCE. Aristotle argued that the medium through which a projectile moves provides the force that keeps it moving. For example, he believed that the air pushes a thrown stone forward, explaining why the stone doesn't stop immediately after being thrown. He distinguished between natural motion, like falling, and forced motion, like a projectile, and believed that natural motion is an object's inherent tendency to move towards its natural place, i.e., earth or water for heavy objects, or a higher level of air or fire for light ones. This motion necessarily needed to follow the pure geometrical trajectories of Euclid's lines and arcs of circles, not the more obscure parabola or other conic sections. Forced motion, on the other hand, required an external force or direct contact to keep the object moving, whether from the medium or the initial push. While no javelineer or archer ever asked the great philosopher for advice on handling their weapons, Aristotle's ideas remain unquestioned truth for centuries. In the 6th century AD, John Philoponus of Byzantine Alexandria, Egypt, suggested a slight modification. Perhaps it was really the stone that kept pushing the stone as it flew through the air. The initial push from the hand or sling provided a motile force that kept the stone moving until depleted, at which point it would fall to the ground. This idea was expanded by the 11th century Islamic scholar Ibn Sina and entered the medieval world's philosophy as the concept of impetus. However, it was the arrival of gunnery and cannon manufacturing in the 14th century that eventually forced a reckoning. First with Tartaglia's attempt to fuse the classical canon with modern observations, and finally with Galileo's outright rejection of Aristotelian physics in the late 16th century through an experimental basis for the law of inertia. The techne of military need finally led to the adoption of the parabola as the true nature of gravity's rainbow, and shifted the question from the ancient what keeps pushing the stone to the modern what causes the stone to stop moving. Even with the Renaissance ballistics beginning the end of Aristotelian thinking, the simple parabola itself was supplanted by the more general theory of orbital mechanics with Kepler, Newton, and other Enlightenment thinkers. Ever more complicated calculations for long-range artillery included accounting for the Coriolis force due to Earth's rotation, considerations of drag and atmospheric variability, rifling for rotational stability, and eventually thrust for rocketry in the early 20th century. Today, our knowledge of projectiles and orbital mechanics has enabled both the intercontinental ballistic missile and the geostationary satellite system, with its need to correct for the effects of Einsteinian gravity. From accidentally dropping an egg off the kitchen counter to planning a multiplanetary slingshot trajectory, we cannot escape the need to study and predict the motion of objects under the influence of gravity. The subject traces a long arc through the history of science and society, and remains of crucial importance in the next frontiers of physics.